What I would like to start with today is an overview of Java's built-in monitor objects. And what we're going to do is we're going to understand what monitor objects do and how they can be used to ensure both mutual exclusion, which we've talked about before and we'll go over again in a second, as well as coordination between multiple threads that are trying to access critical sections of objects. And it's a really cool abstraction, very much the workhorse of concurrency control in Java. So let's first talk about why we need these things. So if you recall, we looked before when we were talking about some of the inherent complexities of concurrency. We talked about some of the problems having to do with scheduling and concurrency hazards. And so we had a scenario where we had this thing called a simple queue, and we would have race conditions in the simple queue. And the reasons we had race conditions was we had producer in one thread that was putting stuff into the queue, and we had a consumer in another thread that was taking stuff out of the queue, and they weren't properly synchronized. And so as a result, you put stuff in, you take stuff out, and there were problems. What we're going to do to overcome those problems is we're going to apply Java built-in monitor objects. And we'll talk about how they address the various problems that we ran into in that kind of example. And you'll get more experience with this as we move further along. So as you can see, we're going to define something just for sake of illustrating the point called a simple blocking queue. And we'll look at a bunch of different implementation aspects of simple blocking queue. In a nutshell, simple blocking queue allows these producers and consumers to concurrently put and take stuff from the queue. And it makes the put and take methods, as well as anything else that you'd want to implement, like isEmpty and all the other stuff that goes along with queues. It makes those synchronized, and we'll talk about what that means. Now, underneath the hood, there's also some other stuff that goes in here. There's something that's called a wait queue, and that's used to do the wake up and sleep stuff that we've been looking at, the notify and wait operations. And there's also something called an entrance queue, which is what guards access to the monitor object in the first place. So that's kind of a high-level view of what we're going to be talking about. And we'll look at all the different nuances, and I'll try to visualize a lot of this stuff. You'll find out that getting this to work properly without a good mental model, literally a mental model of what's going on, is hard. So we'll try to find a way to make it look more clear. Now, what Java implements as part of their monitor object capability is actually something that goes way back to early concurrency research and practice in the computing science field. And it actually goes back to some stuff that were called monitors. Let's see. This is where you can learn more about monitors. And a monitor is basically a concurrency control construct used for synchronization of threads that access some common object. And it allows one thread at a time to have mutually exclusive access to a critical section. So in some sense, this funny-looking little box-like thing here, we're going to see a lot of these examples because this is a way to visualize what's going on with monitor objects. And you'll see that there's this place where you go to kind of wait to get access to the monitor object's critical section. And then you have the actual critical section itself. The rule is there's only ever one thread at a time inside the critical section. And we'll talk about how that's ensured in a minute. And then there's also these other funky things out here. And these other funky things out here are where threads can basically park themselves or wait, block, until conditions become to their liking. And so if you're not able to make progress for whatever reason, like you're trying to acquire a resource and there's none available, as is the case with a semaphore, then you can go ahead and park yourself on a condition in the monitor object. So those are the things you can do. You can have one thread at a time get mutually exclusive access to a critical section, and you can also have a way to allow threads to wait for the conditions to become true. They put themselves off to the side. Of course, you also have a way to allow threads to notify either one or all other threads that are currently waiting on this thing called a monitor condition. The monitor condition is the thing that's used to park yourself while you can't make forward progress. OK, so any questions about the overall abstraction that's going on here? Lawrence?
What would happen if you notified all threads versus notifying one thread? What happens? Because wouldn't only one of those threads be selected?
It depends. OK, that's a really good question. So the question is notify versus notify all. What are the issues? We're going to talk a lot about this in more detail later. But the basic way to think of it is notify will pick one thread. And if you just use the monitor object stuff, it's up to the operating system and the monitor implementation to select the thread it is going to run. And in fact, that's what that specific notification paper is all about. By default, monitor objects give you so-called haphazard notification. So a thread is chosen. I won't say at random, because there could be very well be a good reason for why the thread's chosen that's chosen, but it's not under your control. So that's what happens. You notify something, one thing wakes up. Notify all wakes everything up. And when everything wakes up, then they all come crashing down in what's called the thundering herd problem. All the threads wake up and all come contending, trying to get access to the critical section. Now, the tricky part is only one thread at a time. No matter how many threads have been awakened, only one thread is going to be able to run in the critical section. Now, as to whether or not it's worthwhile waking them up, it really depends on the resources that are being contended for. If, for example, you had a semaphore that had a count that was, let's say that the count was, n, where n is greater than 1, so it's not a binary semaphore. Then if you have a thread wake up, then you might, if you have a thread that wants to let other semaphores, other waiting threads know that there's resources available, there's actually a semaphore operation called release, and you can give it a count, n. You can release n threads. We aren't implementing that for our simple semaphore. We just release one at a time. But there's a Java call called release, and you give it a count of the number you want released. So if you said release n, and where n was big, you might actually want to notify everybody, because they could actually make progress. Because they could come in there, and n threads would be able to get access to the semaphore's resources. So there are some situations where you want to wake everybody up. There are other situations where you just want to wake somebody up, and you don't really care who. There are other situations where you want to wake somebody up, and you know specifically who, and then that's what the specific notification pattern is all about. We'll talk about that a little bit later. So as a rule of thumb, if you are able to have only one thread be awakened, that's what you want to do. Notify is much, much more efficient than notify all. However, especially with built-in monitor objects, there are some limitations with the built-in monitor objects that make it difficult to always be able to use notify. And that has to do with the way that they're implemented. There's one monitor condition for every monitor object. And so oftentimes you end up having to use notify all for reasons we'll show when I give you the illustration of how we might implement simple blocking queue. Jake, do you have a question?
Yeah, is release in, is it just going to notify in?
Yeah.
Okay.
Yeah. You can imagine it might also notify all, and then they'll compete for the things that have been. Release n just puts it just makes the count back to n, and that could be implemented a variety of different ways. You could go n times calling notify, 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 or release, 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 or you could just increment the count to whatever it is plus n, and then wake everybody up. Both of those would be conformant implementations. Okay, so we always try to have human known uses for things. So here's one I kind of came up with. It's not perfect, but it gives you the basic idea. So the idea is you've got an operating room, and the rule is that there's only one person that can be operated on at a time by a surgeon, right? It may be for hygienic reasons. Part of my analogy is going to break apart a little bit here, but you'll get the point. One person at a time is being operated upon. When someone comes to be operated upon, maybe you're doing cosmetic surgery or something like that, you come in here to the check-in room, and they check your insurance card, or that you pay them or whatever. And then you can go in here, and if it's not your turn, right, in other words, if the doctor's already working on someone, you can be shuffled off to a pre-operation waiting room. And so you're kind of off to the side, waiting your turn. And when the doctor's finished, then the doctor puts the people who are finished off in some post-operation waiting room. And so at that point, then the doctor could go and notify and say, hey, bring me another person in to be operated upon. So the key thing here is there's a critical section, which is the operating room, and there are various ways to go in and out of the room. And maybe when you're all done, you leave, when you're all finished. So the problem here is it kind of looks like you're walking through the room, which isn't very hygienic. But you get the idea, right? There's one thing that's going on at a time. If anybody thinks of a better human known use example for this, let me know. That was the best I could come up with. All right, so let's talk about partial solutions. And you'll see that full-blown monitor objects give you some really cool things. Even without the full-blown stuff, you still get a few things, but you really want the full-blown stuff. By the way, does anybody know what this is? And why is it on this slide? So that's actually the Crazy Horse monument. If you look carefully, you can see his face here. And he's pointing, or he will be in 1,000 years when they finally finish this thing. And that's why it's a partial solution. It's not actually done, right? find out more about the Crazy Horse Memorial. So we're going to first start out by having something called busy synchronized queue. And this is going to be a partial solution. As you can see, busy synchronized queue implements blocking queue, which is sort of the root of all the queues. All the blocking queue mechanisms available in Java's concurrency libraries implement blocking queue, and they get an interface with methods like put and take and so on. And the basic rule is with synchronized methods, only one of these things can be active within an object at a time. So it doesn't matter how many threads are calling these methods, only one of them are going to be, only one thread at a time will be running. And we'll talk about how that happens in just a second. So when you add the keyword, when you add the synchronized keyword, two things happen. The first thing happens is that put and take operations cannot interleave. Remember when we had talked a class or two ago about atomicity, and I showed you the volatile keyword, and we talked about how volatile allowed you to do atomic assignments, atomic reads and writes to basically any kind of primitive variable, be it an int or a long or double and so on. And we talked about how I++ or I were actually not atomic operations because they had multiple steps. And if you had two threads running at the same time, those steps could actually interleave. Remember we talked about all that? So what making something synchronized means that put will run atomically, and it'll be done. And then take will run atomically, and it'll be done. And so they can't occur where a little bit of put goes and a little bit of take goes. They're sort of either, they all run and they all block everybody else out until they're done. So interleaving can't happen. The second thing is more subtle, but it's very important. And if you recall, we talked about volatile, we talked about cache effects. We talked about how if you have a system with multiprocessors or multi-core, then the memory has to be cached and the caches have to be managed. And so the other thing you get when you synchronize methods is you get this so-called happens before relationship. And what that says is that when this method is finished running, then any state that it changed will be flushed out to the cache so that somebody else who comes along later and runs will see the newly visible value. And that's what's called a happens before relationship. So you're ensuring the visibility of state changes to all the threads in the system. So it's basically making all the caches have the same value. Whenever you reach the end of this synchronized method, the enclosing, closing curly brace, that flushes all the state that was changed out to other threads. And when they come along and they do a synchronized operation, that will then make sure that they start out with a consistent value. So synchronized is really doing two things for you. It's making sure stuff occurs in the right order, and it's also flushing the caches properly as well. Volatile does the cache flushing, but it doesn't prevent the interleaving of multi-step operations. Okay, any questions about any of that? Lawrence?
What kind of operator is just a question mark without a ternary colon?
Oops, that's called a syntax error operator. It's a very common operator. I see it a lot in programs that people write. Let's fix that.
Thought I was learning something new about Java.
I wish that could be the answer. Great. All right. Well, I will go back and fix this later. That's great. That's called a persistent presentation. You can't fix it once you've. All right, that was weird. This is a consequence of having things that are shared between PC and Mac. There's a really nice article here that talks about synchronized methods and explains in nice, concise details what we just talked about. Now, this will give us mutual exclusion, but there's still big problems with this particular solution. And the problem is that if you have multiple threads calling these methods, they will not be corrupted, but they will end up busy waiting. Because if the queue is empty or full, either it's empty or it's at its capacity, then it'll go ahead and just keep returning and busy wait. Here's more about busy waiting. So busy waiting basically means that rather than putting yourself to sleep when you can't make forward progress, like the queue is empty and you want to get an item out of it, busy waiting just sits there and goes, is it there, is it there, is it there, is it there? And it's like talking to a hungry puppy or something, right? They're not going to be placated until you feed them. And they will sit there and just harangue you until you give them food. OK, So this is the partial solution. So synchronized methods get us part of the way there, but they don't solve the whole problem. So what now we're going to do is take a more systematic view of monitor objects and see how they go a little further. Now, the way it works in Java is that all Java objects can be monitor objects. You just have to use them as monitor objects. So they all come well equipped with their monitor objectness. And what that means now, of course, if you don't use synchronized, the features aren't used. And maybe, in theory, a virtual machine could optimize this stuff away. I don't know whether it does or not, but that's an implementation consideration. But at least in theory, it could act as though it was going to take away some of the overhead here. There's a really nice article here at this link that talks at length about what we're about to cover. So I'd recommend reading it if you want a deeper understanding of some of this. So the two things, mutual exclusion and coordination. So let's talk about them one at a time. So mutual exclusion says you get this lack of race conditions. You're going to have the happens before relationship. You're going to prevent interleaving, all those kinds of good things. And that's implemented internally by the it's implemented by putting the synchronized keyword in the right place or places. But how it's implemented under the hood is by something called an entrance queue. And the entrance queue is basically what gives Java its so-called intrinsic lock capability. So every Java object has a so-called intrinsic lock. So what that means is you don't have to define it externally. It just comes along for the ride. And you'll see how it gets used. If you have a method called synchronized, then it's synchronizing on the intrinsic lock. If you use synchronized statements, or sometimes known as synchronized blocks, it's more clear what's being synchronized. And we'll take a look at that in a second. Under the hood, the Java virtual machine implements the entrance queue. And if you take a look at the Dalvik implementation that's currently the virtual machine on Android till they replace it with the newer version, ART, Android Runtime, you'll see how it all works under the hood. I'll talk about how it's implemented shortly. The second thing is coordination. And that's what allows the threads to cooperatively schedule their interactions so they can run in various times. This is done by something called the wait queue, which again is supported by the Java virtual machine. And you have a wait queue, and you have these methods, wait, notify, and notify all. We'll talk a bit about those. We'll talk about how they compare and contrast to other mechanisms that are available in Java. They don't call it this in the documentation, but you could call it the intrinsic condition. So you have an intrinsic lock, which is talked about a lot in the Java documentation. And every monitor object also has one and only one intrinsic condition, which is typically called the monitor condition, as you'll see in a second. OK, so that's basically the structure of how all this stuff works. These mechanisms implement something called the monitor object pattern. And we're going to talk more about this pattern later. You can download the PDF of an earlier version. This is actually from the POSA 2 book, but you can download an earlier version of the pattern here. And the intent of this pattern is to ensure only one method runs within an object, and the pattern allows the object's methods to cooperatively schedule their execution sequences. That's what the pattern does. Now, the interesting part about this pattern is you don't have to implement it using monitor objects. You can also implement the monitor object pattern using more primitive synchronization mechanisms that Java provides. Maybe primitive is the wrong word. Additional mechanisms that Java provides for concurrency. And those would be things like reentrant locks and condition objects. And very soon, probably maybe this Wednesday, maybe next Monday, we'll start talking about some of these mechanisms, reentrant lock, condition object, and so on, because they're important to know as well. They're the building block pieces that Java programmers use to write concurrent applications. Typically, the JVM implements the stuff at a lower level. OK, so we can use these monitor objects to come up with better solutions than our buggy queue, which had no synchronization whatsoever, and our busy synchronized queue, which busy waited too much. So this is what the mechanism is going to be. We're going to talk about the entrance queue. We're going to talk about the wait queue. And later, we'll talk about the monitor object pattern. We'll probably talk about that at the end of this discussion about Java concurrency mechanisms. It's really important to understand the pattern because the pattern tells you when and how to apply the various pieces. So we're going to talk a lot about the mechanisms. It tells you how to apply them and how to apply them correctly. All right, so let's talk about the easy part first. Synchronized methods and statements. And you'll see those are both, they're different things, but they both do important stuff. To make this discussion concrete, we're going to have something called the simple It should be simple blocking queue class. If I could edit my slides, I would. Simple blocking queue class. And as again, that implements blocking queue. And it's got some internal state. And this internal state, of course, has to be protected against race conditions because it doesn't have any locking intrinsically, or doesn't use the locking intrinsically. mlist is a list of whatever we're parameterizing this thing with. And capacity is just a count of the number of elements that are the maximum that can be in this queue. And then the constructor obviously initializes all this stuff. So you can see it makes a new array list, which is not bounded by anything, and it keeps track of the capacity. If you want methods to be synchronized, the easiest way, although by no means the only way, and often not even the best way, is to put the word synchronized in the signature of the method itself. So this is what we could do here. We could have put, take, and isEmpty all be synchronized. And if you do that, then they're all serialized with each other. By the way, what happens if you have synchronized methods and non-synchronized methods in a monitor object? What's the consequence of that? Just by looking at the signature, without looking at the implementation, if you just look at the signature of a Java class and you see methods that do not have the word synchronized, what does that tell you?
Red, they can be, they can go multiple threads at once, even if you're waiting on something else.
So it actually was a trick question. It doesn't tell you anything. Because as we'll see in a minute, there's things called synchronized blocks or synchronized statements that could be used in the implementation. But when you see something that's synchronized in the signature of the method, in other words, it shows up here in the method name or the method signature, then you know it's synchronized. You know the entire method synchronized. If you don't see the word synchronized, then you're not quite sure what it does, and you have to dig a little deeper. Maybe look at the source code, hopefully read the documentation, hopefully it'll tell you what to do. As a general rule of thumb, if you have synchronized methods in a class, you probably don't want to have unsynchronized methods, in other words, methods that have no synchronization, unless those methods are only called from within synchronized methods. Like you might make them private, for example, and then they couldn't be called by anything except the public methods. So that would be a good design tip to keep in mind. The analogy, we've talked about this before, is of synchronized is basically a protocol for accessing a resource where you just want one party in at a time. So vacant occupied like a restroom in an airplane. And we'll talk more about that when we talk about reentrant lock. That'll be our human known use for reentrant lock. So when you use the method, when you use the keyword synchronized in the method signature, the entire body is synchronized. So this is a good example. isEmpty checks to see if the list is 0 sized, and that whole thing is synchronized. You can also have what are called synchronized statements. And that means that just the block is synchronized. Now, in this particular case, the entire method is one synchronized block, which is basically the same as this, except it's not appearing in the signature. So the synchronized keyword is not appearing in the signature. What might be a reason for not putting the synchronized keyword in the signature? Even assuming you want to make them synchronized. Yeah?
Well, if you want to only synchronize a certain, like a small part of the code.
Great, and we're going to see that in just a second. So synchronized statements enable more fine-grained serialization than synchronized methods, because in this particular case, it doesn't help because it's just one thing. But in other examples we'll look at, you might actually break it up into multiple sections, and you would get more fine-grained synchronization. So that's a very good answer. So if you make it synchronized method, then you're sort of synchronizing the whole thing. If you don't, you could have synchronized blocks. What's another reason for not putting synchronized? Jake?
If you want to synchronize it on a different block or different object other than this.
If you want to synchronize it on something other than this, or if you want to be able to use something other than the monitor object synchronizer, right? If you want to be able to use a reentrant lock or something else, like a read-write lock or whatever. That would be another reason not to make it part of the keyword. In this particular case, the statement is serialized on this, which is the so-called intrinsic lock. You can also, and this is what you actually do in your simple semaphore that you're implementing for assignment 2A, you're actually implementing an object, and you can synchronize on that object itself. Keeping in mind, of course, that is because every object itself can be synchronized, right? Every object is a monitor object if you so choose to treat it in that way. Okay. So that's basically synchronization. Now let's talk about built-in waiting and notification mechanisms. So as we talked about before, synchronized methods were better than nothing, right? But they were a partial solution. So now we're going to talk about the complete solution in this context. So monitor objects allow us to be able to coordinate the interaction of threads cooperatively. And what that means is that all the parties have to be part of this game. If one party decides they don't want to play by the rules, everything falls apart very quickly, and you'll see how that would work. I should also hasten to note that usually when you're using these mechanisms, they're layered underneath of a higher level abstraction, like a semaphore or a queue or something like that. You very rarely access these things directly for other reasons. So here's an example. We're going to talk more about the implementation of these methods in more detail in a minute, but just at a high level, there's a bunch of methods: wait, notify, and notify all. And wait, which is the way you put yourself to sleep until a condition changes according to what you want, is actually something that's called it's an implementation of something called the guarded suspension pattern. So if you go to this Wikipedia link, you can read about guarded suspension. And the guarded suspension pattern basically manages operations, this is an example of one, that require two things. They require a lock to be acquired, in this case it's the intrinsic lock, and they require a precondition to be satisfied before you can make forward progress to carry out the operation. So in this case, for example, we're trying to put something into the queue. And while the queue is full, the precondition here is queue is not full, right? That's the precondition. So while the queue is full, we have to wait. So that's guarded suspension. You can't make forward progress until the queue is no longer full. And this is just a quick check to see if the queue is full or not. And only when both those conditions are true, you hold the lock and the condition is true, can you proceed on to the next step. Very, very important to understand that. That's one of the interesting, I won't say quirks, because it's not a quirk. It's one of the charming aspects of conditions and monitor conditions, is that they can put themselves to sleep, they can block until something changes that is in their liking. Now this is why it's cooperative. If nobody comes along later and wakes anybody up, then this guy will just keep sleeping forever. So this requires cooperation between publishers and subscribers, or producers and consumers. They have to agree to obey a protocol. Now, we'll come back and talk about this later, but you'll notice that after we stick something onto the queue, after we put something on the queue, we're going to notify everybody the state may have changed, that they may be need to know about. Can you think of somebody, what type of a method might care that the list that we're using to implement this queue now has a new element in it? Who would care about this? The take method, right? The take method, which we're going to look at in a minute. The take method cares because the take method is part of this cooperative process, and it's not going to be able to make any progress if it's trying to take a method from an empty queue until somebody put an item onto it. Now, you'll see later on that there's some weird quirks about Java's one and only monitor object per monitor condition per monitor object that makes us have to use notify all here. And it's kind of a pain and it's kind of inefficient. So you'll see later when we talk about Java condition objects, we can optimize this quite a bit. This is actually very inefficient. Nobody would ever write production code like this if they could avoid it. OK, every Java monitor object has one wait and one entrance queue. So here's sort of a picture. This is our simple blocking queue, one wait queue, one entrance queue, producer, consumer. There could be a multiplicity of these things, of course. Surprise, surprise, if you call wait, that's done on the wait queue, right? So you call wait, and that basically puts you to sleep on the wait queue. This is all handled underneath the hood. Again, surprise, surprise, when someone calls notify or notify all, that also applies to the wait queue. In fact, in some sense, you're building something along these lines in your simple semaphore. You're building a wait queue that people are waiting on in a specific order, and then you're waking them up in a specific way. Having only one wait queue is more restrictive than programming with condition objects. And again, we'll talk about that more later. The consequences of this we'll talk about in part 2 in just a minute. Under the hood, Java implements the built-in monitor object synchronizers via POSIX mechanisms. Does anybody know what POSIX is? What does POSIX stand for? it's a standard which is standardized by the IEEE, and I think the Open Group is involved in this somehow as well. And it basically is portable operating system for Unix. So they basically standardize the way in which Unix system calls and system functions are defined so that, at least in theory, you'd have an easier time moving things between different vendors' platforms. And they use POSIX mechanisms. They use something called a POSIX mutex with recursive locking semantics, which gives you this recursive feature we'll talk about later when we talk about re-entrant read-write locks. Does anybody know what it means to be a recursive lock? Robbie?
It means that if you hold the lock, you can reacquire it as many times as you want, but you have to also release it as soon.
Right. So exactly. So a recursive lock is a lock where if you are the owner of the lock, you can acquire it again without deadlocking on yourself. And the only catch is you have to release the lock the same number of times you acquire it. Otherwise, it'll remain locked. What's the opposite of a recursive lock? A non-recursive lock. Okay. What is the characteristic of a non-recursive lock? What happens if you try to acquire a non-recursive lock?
Deadlock.
Something bad will happen. Maybe it'll deadlock. Maybe your program will crash. It's a bad thing. Why do you think people have non-recursive locks? What on earth? Why would you do that? If a recursive lock gives you this cool property of being able to be reacquired, why would you ever want a non-recursive lock?
Because you don't want it to be reacquired.
One thing might be you don't want to be required, right? So you want to prevent people from even doing that or have it be a failure. Yep, that's good. Because that could actually indicate a bug in your program, by the way. What's another reason why you might want to have a non-recursive lock? Well, you will find this out if you ever have to implement one. You discover that a recursive lock implementation is more complicated and much, much, much less efficient than a non-recursive lock. Non-recursive locks can use very, very efficient hardware test and set operations or compare and swap operations, so they're really, really fast. The downside, of course, is that they don't have the re-entrant semantics, but the upside is they're really fast and arguably less error prone, but that depends on what you're trying to do. So anyway, that's what they use, and you can go here and read about mutexes if you want to learn more about them, and pthreads, which we talked about before. Remember we talked about pthreads as an example of accidental complexity? Well, the deal is it's accidentally complex, but if you're using it to implement the virtual machine, that's somebody else's problem, not your problem as a Java programmer. A wait queue is implemented as a POSIX condition variable. You can have a bunch of things waiting on this, and in some sense that's a little bit like what you're doing with your simple semaphore, and you can read about condition variables here. POSIX condition variables are similar to Java condition objects, and we'll talk about those and compare and contrast them later. Obviously, they're written in different languages, though. If you want to read the source code for this stuff, it's in the Android release under Dalvik, VM, and sync.h and sync.cpp. So they implement these things in C++ for Android. So Java code that does the locking and unlocking stuff at the monitor object level, the built-in monitor object level, is actually running native C++ code. Jake?
Yeah, so the wait queue, that's a little bit of a misnomer, right? Because it's not fair, right? Or is that
Just because something, if you've ever been standing in line and someone cut in front of you, you were standing in line, but it wasn't fair, right?
is the entrance queue fair?
Is the entrance queue fair? I believe the semantics of that are not really nailed down either, so it might not be fair either. Here's an example of why you might not actually want things to always be fair. The reason you might not always want things to be fair is because you might have something that's higher importance and you want them to cut ahead, right? So if you're driving and there's an accident, you want the police cars or the fire truck or the ambulance to cut ahead of you in line, right? You don't want them to wait in the line. If you are a bartender at Miramar, which is where Top Gun was filmed, and you're serving officers in the bar, you want to serve the generals ahead of the colonels, ahead of the majors, ahead of the captains, right? So you may show up in different order, but you want to serve them in the order of preference or priority or rank or whatever. So there are reasons why fair is actually not always a good thing. In fact, fair is actually often a very inefficient thing. And you'll discover that when we get a little further along. You'll discover fair implementations of things are typically way, way more overhead to implement than unfair things. So you only do it when you really need to.